Section 4.7, Maxima or Minima problems. Just like in Calc 1, you learned how to find the max or min of a function using derivatives. We're going to see how that works in Calc 3 with functions of 2 or more variables. The idea of critical points from Calc 1 came from watching the slope of the tangent line transition from a positive slope to a zero slope to a negative slope, or the opposite way around where you went from negative to zero to positive. We said that that would only happen if you were at the top of a hill or the bottom of a valley. So to find our critical points, we took the first derivative, set it equal to 0, or we took the first derivative and found out where it does not exist, and that's how we found our critical points. If we're talking about local extrema, we are zooming in to a small window. For example, if I were to, let me erase here for a second. If I were to pick the interval between the red bars that I've drawn, this hill on the left looks like the maximum. And if I were to move that right boundary all the way to the other side of this other hill, that maximum that I picked wouldn't look like the maximum anymore. This one would. So a local extrema depends completely on the interval that you're looking within. So to find your local extrema, you would first find your critical points, then find an interval around that critical point so that you could say within this interval the max that I found is the real max, or reverse the argument for a minimum. For Calc 3, the idea is very similar. We will find the critical points using derivatives, but now instead of using a regular derivative like from Calc 1, we need to use our partial derivatives. So for a function of 2 variables, we would need to look at both first-order partials, set them each equal to 0, and then find our critical points from here. Now this is slightly different than from Calc 1 because we're not looking for an interval within which the function is always larger than its surroundings or less than its surroundings. Now instead of an interval, we are looking at a disk. So we've got the disks drawn out here on our surface, and we're saying that within that disk, this red dot looks like a maximum. So it's not an absolute, it's just relative to the disk that you find. Let's practice finding some of these local extrema for a function of both x and y. First thing we're going to do is calculate our partial derivatives. Partial with respect to x, we need to use our chain rule. So we have 1/2 from the square root function. Keep everything in the inside. Reduce the old power by 1, so that gives us a negative 1/2 as our exponent. Then multiply by the derivative of the inside with respect to x. So the y terms zero out. And we can rewrite this as negative 18x plus 36, all divided by 2 times the square root of 4y squared minus 9x squared plus 24y plus 36x plus 36. So that is our f partial. We need to repeat this process for the y partial. I would encourage you to try this on your own. I'm going to pause the video and write out my work. I would encourage you to pause the video, check your work with mine when you're done. So I have my partial with respect to x. I have my partial with respect to y. Oh, I'm missing a 2 on this one. Must have accidentally erased that. And to find our local extrema, we're looking for the critical points by taking each of these first-order partials and setting them equal to 0. Once we set these equal to 0, we don't really need this f of x partial notation anymore, or the fy partial notation either. We're simply trying to solve this system of equations. Now, anytime you have a rational function inside of your equation, the first thing you should do is try to get rid of the denominator. Notice that both of these equations happen to have identical denominators. So I'm going to use the denominator, the LCD, or you can call it whatever you want. It doesn't have to be LCD. I'm going to multiply the denominator to both sides of the equations because on the left it would divide it off, and on the right it would give me equal to 0. Same thing for the partial with respect to y. Multiply both sides by the denominator, greatly simplifying our equations here. Now we're looking at negative 18 x plus 36 equals 0, and 8y plus 24 equals 0. Solving this system is going to be quite easy because notice that each one of the equations we're looking at has only one variable. We don't have one equation with both x and y in it. So we can solve each one of these little equations. We can see 36 is equal to 18x, which leads us to see x has to be positive 2. And then from the other equation, we can see 8y equals negative 24, leading us to see that y needs to be negative 3. So we found one critical point at 2, negative 3. But we also have to check to see if the denominator of those partial derivatives was ever equal or was ever undefined. So let's go back to our partial derivatives before we cleaned them up with the LCD and ask ourselves, is it possible for these to ever not exist? Meaning, does the denominator ever equal 0? So we need to check that on each one of these. Because they have the same denominator, that's going to make our job a little bit easier. So let's copy down our denominator here. So I've copied down our denominator at the top of the screen. We're going to check to see if it's ever equal to 0, because if it is, then the derivative is undefined or does not exist, which is another criteria for a critical point. So as we look at it, it might feel a little bit overwhelming to say, oh, I don't know if that's ever equal to 0. But if we just do a little bit of algebra manipulation, we can figure this one out. So let's start off by dividing both sides by 2 to get rid of our 2. 0 divided by 2 is still 0, so this hardly makes any difference. Let's also square both sides to get rid of our square root. 0 squared is still 0, so that just drastically made our equation much simpler. And now I want you to notice that we have y squared and y terms. We also have x squared and x terms, which means there's a potential here that we could use completing the square to simplify this expression. I'm going to refer you to the textbook on this one because this is an algebra thing that most of us have probably forgotten, but a quick read through on this would help you out. So let's take you to page 439 if you want to see all of the steps to work this down. But essentially, this turns into a hyperbola of this form, which means any points along this hyperbola would also be considered critical points for this function. So any xy that satisfies this equation would also be a critical point, the same way that 2, negative 3 was a critical point. Now let this remind you that when you're solving a system of equations, that you not only need to check when the partials are equal to 0, but also to see if the partials are ever undefined. Let's take a look at another example. Again, finding local extrema for the function f. This time, we have a slightly different definition for f, but the process will be the same. So we're going to find our first order partials. Here's my partial with respect to x, partial with respect to y. We're going to set each one of these equal to 0 so that we can solve the system and find any possible critical points. This system equations does involve linear equations with both x and y in them. So to solve this type of system, we can use substitution, elimination, a matrix. Think back to your pre-calc days when you were solving these kind of systems. Pick whichever method you like. I'm going to use elimination. I'm going to take the first equation and then subtract the second one. So I'm going to rewrite that over here on the right. Subtracting the second equation is going to change all of the signs on my terms. The x terms are eliminated. My y terms, I now have 10y. And then for my constants, I have plus 10 equals 0. And solving this shows that y has to be -1. If y is -1, then we go back and check to see what x would have to be. From the first equation, we would have 2x plus 2 times -1 plus 4 equals 0, or 2x minus 2 plus 4 equals 0, or 2x plus 2 equals 0, or rather, x equals -1. So we were able to find a critical point at -1, -1. Just for good measure, let's talk for a second about whether or not either of these partial derivatives could not exist. So looking at each one of these, they're actually just polynomials, and there's nothing in the domain that would cause these partial derivatives to not exist. So we only have the single critical point at x equals -1, y equals -1. One of the theorems presented in this section is Fermat's theorem for functions of two variables. It basically says if you have a function z that takes in an x and a y, and it's defined on an open set, right, all of the mathematical jargon here, basically it's saying that if there is a local extremum, like a max or a min at this point x0, y0, then that point has to be a critical point. This can often be confused for saying the opposite, meaning reading it backwards. So be careful. Having a critical point does not guarantee a local extremum. The reverse is what's true. Having a local extremum guarantees that you have a critical point. Let me show you what I mean. Let's look back at a Calc 1 function like x cubed. This function has a critical point at x equals 0. If we were to take the derivative, we'd see it's 3x squared, set that equal to 0. We find that x equals 0 is a critical point. But if we look at the function, oh, that's not a perfect graph, but if we look at the x cubed function, x equals 0 is right here. It's an inflection point. It's not a max or a min. The derivative is positive, positive, positive. It never changes sign. So this is one of those like fake out critical points, and we need to be careful of that even with our multivariable functions. So we have a critical point, but it does not guarantee that there's an extremum there. We always have to test these critical points, and in Calc 1 we had two options. We had the first derivative test, where we would put our values on a number line and test around it, or the second derivative test, where we would calculate the concavity at each critical point And if you had a second derivative that was positive, that means it was concave up. If you had a second derivative that was negative, that means it's concave down. So we had to pick between these tests to be able to classify if we had a max, a min, or neither. In Calc 3, we can have a similar but different issue. So here, we have a critical point at the origin. But if you look at the traces, the vertical traces, along the y direction, we get a downward facing parabola. You see that in magenta. Along the x direction, we have an upward facing parabola. You see that in light blue. And these two things don't agree with each other. In the x direction, it's saying that we have a minimum. In the y direction, it's saying we have a maximum. This is something we never dealt with in Calc 1. It's a new issue to Calc 3. We call this situation a saddle. It's not a max, it's not a min, it's neither. It's a saddle. So now if we wanted to test these critical points in Calc 3, rather than picking between the first derivative test or the second derivative test, we have a new test. It's also called the second derivative test, and it still requires both of your partial derivatives to be equal to 0. But this new part, you're going to calculate a discriminant. It uses second order derivatives. So we have the second order with respect to x, second order with respect to y, and the second order mixed partial. If you're curious about where this comes from, chat with me in office hours. I'd be happy to show you where it comes from. You calculate this discriminant at each of your critical points, and then you check which of the three cases you have. If your discriminant is positive, you either have a max or a min. To figure out which one you have, you simply look at either one of your second order partials, either the second order with respect to x or the second order with respect to y. You don't look at the mixed partial here. If your discriminant is positive, just go back and look at either one of your second order derivatives and check. If the second order derivative was negative, then you have a max, just like the picture I've drawn here. Two negatives for second order derivative being negative and a sad face to say that we have a maximum at the top of that. However, if your second order derivative was positive, then you have a minimum, just like the little face I have here. The smile has a minimum at the bottom. So you calculate your second order derivatives, create this discriminant, plug in your critical point. If your discriminant comes out to be positive, then you need to check one more thing. That's the second order partial with respect to x or y, doesn't matter, and decide from there. However, if your discriminant is not positive, if your discriminant is negative, then that's a saddle point. You don't need to check anything further. That critical point turned out to be a saddle. And then the last case, if your discriminant was not positive, if it was not negative, if it's simply 0, this test fails. It doesn't say that we know anything. It says we know nothing. So if you calculate the discriminant and you get a 0, then you have to find a more clever way to decide if this is a max, a min, or a saddle. The problem-solving strategy that goes with this second derivative test says first, find all your critical points. And then we're going to discard any of the points where at least one of the partial derivatives does not exist. Next, you're going to calculate the discriminant at each critical point. Then you're going to apply the second derivative test, meaning you're going to check to see what the discriminant value is. Is it positive? Is it negative? Or is it 0? Let's do an example of using this second derivative test. We want to find all the critical points, and we want to use the second derivative test to find the local extrema. So not only are we finding our critical points, but we're going to classify them as max, min, or saddle. So we need to calculate quite a few derivatives. We need the partial with respect to x, the partial with respect to y. We'll use those to find our critical points. But then we also need the second partial with respect to x, second partial with respect to y, and then the mixed partial. And we need these for the discriminant. So let's go ahead and calculate these partial derivatives. I'm going to pause it here, write out my partials. I would like for you to pause the video, try it yourself, and then compare answers. I've got all of my derivatives worked out, so let's go ahead and find our critical point. We need to take our first order partials, set them equal to 0, solve this system. I can see x needs to be equal to -1, y needs to be equal to 2. So we have one critical point at -1, 2. Now we want to classify it. So we're going to create the discriminant, which uses our second order partial with respect to x, which I found to be 8, times the second order partial with respect to y, which came out to be 18, subtract the mixed partial squared. So the mixed partial was 0, I'm squaring 0 here. Now, sometimes the discriminant is filled with constants, like in this case. And so you're not actually plugging in the critical point, x equals -1, y equals 2, but that's not always the case. We'll see that later. For now, calculating this discriminant, we can see that this is definitely going to be positive. If the discriminant was greater than 0, we need to go back and check either one of our second order partials. We could look at the second order partial with respect to x or the second order partial with respect to y. And it doesn't matter which one you pick because those two partials, the second orders, both have to have the same sign in order for the discriminant to be positive. It's not possible to have second order with respect to x negative, second order with respect to x, y positive, because if you multiplied a positive and a negative right here, your discriminant's automatically negative. But in this case, they're both positive. We have a discriminant that's positive. We go back and we say, oh, second derivative was positive. That must mean we have a minimum. So we have a minimum at -1, 2, and if we wanted to find the actual extreme value, we would plug that into our function. Plugging x equals -1 and y equals +2 into our function, we can find the minimum value of f. And we see that the minimum value of our function at x equals -1, y equals +2 comes out to be -16. Let's do one more example, again using the second derivative test. So we know we need our x partial, our y partial, our second order x, second order y, and our mixed partial. After we calculate each of the derivatives that we need, we can create the system of equations where our first order partials are set equal to 0. Using whichever method we want to solve this system. I'm going to add the two equations together, add the opposite, so I can eliminate the two y terms. That will get rid of my y terms. I'm left with x squared minus 2x minus 3 equals 0. Then I need to solve this equation to find our critical points. We can do this one by factoring. We see that x is either equal to +3 or x is equal to -1. So we have two potential critical points. We need to plug each one back into our system to find the corresponding y values. So if we use the first equation, we'll see 3 squared plus 2y minus 6 equals 0. That would say 2y equals -3, or y equals -3/2. And we can plug -1 in. We get -1 squared plus 2y minus 6 equals 0. That looks like 2y minus 5 equals 0, or y needs to be 5/2. So we have our two critical points. We have 3 with -3/2, or we have -1 with +5/2. Each one of these needs to be tested using the second derivative test, so let's calculate our discriminant. The second order partial with respect to x is 2x. Second order partial with respect to y is 2, minus the mixed partial, which was 2 squared. And then we plug in our discriminant, so our points. At x equals 3, y equals -3/2. The discriminant looks like 2 times 3 times 2 minus 4, or 12 minus 4, which is positive. Since this discriminant is positive, we need to go back and look at the first order partials. We had the second order with respect to x was 2 times x, but x is 3 in this case. That became a +6. And for good measure, let's look at the second order partial with respect to y. Notice that's also positive. So it doesn't matter which one we look at. If the discriminant is positive, you just need to check one or the other. Both of us tell us that we have a positive second derivative, which is a minimum. Now we need to test the other critical point. So at -1, 5/2, we'll calculate the discriminant again. That becomes 2 times -1 times 2 minus 4, or -4 minus minus 4, which gives us -8. In this case, our discriminant is negative. So we know from the second derivative test that we just found a saddle. So these were examples of how to use the second derivative test in Calc 3. It's a little bit similar to Calc 1, but also quite a bit different. We didn't use the discriminant the way that we're using it now. Try some examples and let me know if you have any questions.